So up until now, our picture of the populations has just been two populations. Now it's the same thing, we're just adding in a third. But our hypothesis is still in regards to our populations, determining whether or not our populations are really no different from each other. So our samples all belong to the same population. Remember, we talked about the terminology, the factor being your independent variable, the one that's manipulated. It's always nominal scale of measurement. The levels are the groups within that factor. So you might have 3 different types of learning styles, or 3 different kinds of treatment you're assigning participants to. That's your levels. Your dependent variable is your outcome variable. It's what you're measuring. It's what you're the response from the participant. And it's usually interval or ratio. And a factorial design is when we have more than one factor, which you won't have in this chapter or this class. Our null hypothesis extends to the third population, saying that all 3 populations are equivalent. So there are no differences between our populations. Our alternative hypothesis always says there's at least one mean difference among the populations. It doesn't ever specify where that difference is. It just says there is one. So you don't need to specify which mean that you predict is going to be higher than which other mean. That's not what the ANOVA is testing. It's testing just whether or not there's any mean difference. Okay, so it can be wrong with just one group being different from one other group, or all the groups could be significantly different. There are many ways that the null hypothesis can be rejected. So up until now, all of your t-tests, even the z, looked at a sample mean difference, the mean from the population, or the mean from another mean, or the repeated measures was a before to an after. It was some kind of mean difference over error. We call that standard error. Well, now we can't look at mean difference, so we look at differences among the sample means by way of their variability. So we expect that the variability will be high between our means, because we want to show that our means are largely different from each other, and so the difference between them will be high. And if that's the case, then our variability will be high for that between group difference. And the within group difference, that's the people within each group. We want all of those people to represent their mean by being closely clustered around the mean. And if they're not, if they're very spread out, then that within group variability will be high, and so your denominator will be high. So the large F ratio that you want to obtain in order to reject your null will have a large between group variability, which is your numerator, and a small within group variability, which is your denominator. Okay, so we talked about this. We talked about why we don't do multiple t-tests. We don't want to inflate our T1 error, type 1 error. We want to keep alpha and type 1 error at 0.05. Okay, so we talked about how we're partitioning the total variability. We have 100% variability in our experiment. Our experiment can account for 100% of the variability. Some of that variability will be due to our effect, so it will be explained by our effect, and some of that variability will be unexplained by error. Okay, so we're going to partition that total variability into the amount due to our effect, which is our between group, and the amount due to individual differences or error, which is our within group. We want between group variability again to be high. This indicates that we have a strong effect. The within group variability again is how much the scores within each group vary around their mean. So if you're my sample, remember I was comparing 3 different stat courses, and if I want to look at your stat course compared to, say, my spring semester, I want your scores to be closely representative around our mean. So if our mean score is an 80, then I want that within group variability. I want all of your scores to be tightly clustered around the mean of 80. If it's not, if your scores range from 50 to 100, then that within group variability is going to be difficult to tell whether or not 80 really is a good number for your group. Whereas if you're comparing it to another class and their average is 90 and all the scores are very tightly clustered around that 90, then they belong to a very distinct population. Okay, when there's a large spread, it's difficult to be able to determine whether or not they really belong to a separate population. And that's what this visual is trying to represent. So in the first example, we have two groups. We have a 4-point mean difference, so you see the between group variability very clearly, and you also see the within group variability is very small. All the scores are clustered around their mean. So you can very clearly see that they're two very separate groups. In the example B, you still have a 4-point mean difference, but the scores overlap. There's a lot of within group variability. And what that does is it kind of obscures the effect. So you can't really see if there really is two different populations. It really looks like just one. Okay, so we are going to look at the sources of variability. We're going to assign them to the appropriate sources, and then we're going to conduct an F test to determine whether or not our between group variability really is high enough to be greater than what we would expect by chance. Okay, it's above and beyond our error. Okay, we still have a little bit of error in our between groups, so there's still, even in our manipulation, there's going to be some error due to our own experimental errors. There's going to be some individual differences. Remember I said that there's error in both of these sources of variability. So when you cancel that out, let me find this here, this slide right here. So when that error cancels out, because it's the same error, you're left with just your effect. So is your effect large enough to reject the null? Well, your null says that that effect is 0. So if that effect is 0, then your F ratio should be 1, because error divided by itself is 1. However, once you cancel out error, that effect, what's left, that variability, is that variability large enough that we can reject the null? And because it's variability, it's always going to be positive. So we're always looking at a one-tailed F critical value, and once we reject the null, we conclude that there is at least one significant difference among our means. Okay, we can't really pinpoint where it is yet. Okay, so if the null is true, our F is near 1. If the alternative is true or our null is rejected, we'll have a noticeably larger F value. It will surpass our critical value. Okay, we went over this. If the null is true, we expect F to equal 1. If the alternative is true, we expect F to be greater than 1. Significantly greater than 1, not just a little over 1. It has to be greater than our critical value. So this is where we started to get into our examples, where we went through the formula. This is just notation to get you ready for the ANOVA formulas. It can be kind of overwhelming, but once you work through a few examples, it will become a lot more second nature. So let's just get to the formulas. So again, recognize that we're splitting up the variance between the treatments, between our groups, and within our groups. So variance, the formula of variance, is sums of squares over degrees of freedom. So we're going to have a variability, which is sums of squares over degrees of freedom, due to our between group and due to our within group. So we have to calculate our sums of squares between and a sums of squares within, as well as the degrees of freedom between and a degrees of freedom within, in order to get that variability between and within. Okay, so we start off with the total formula, which is variance between and variance within. However, our variance formula breaks down to sums of squares between over degrees of freedom between and sums of squares within over degrees of freedom within. Okay, But this variability, because all variability totals 100%, the between and within variability, sums of squares total, the sums of squares total. Same with the degrees of freedom. They add up, they sum to the degrees of freedom total. Okay, so the formulas are here. Remember, G is the total number of scores, and all of your x's added up. The sum of your x squared, this value right here, is all of your x's squared and then summed. Your t is the sum of your x's within each group, and you can sum all of your t's in order to get g. Okay, so these are just very straightforward formulas. You shouldn't need a whole lot of memorization with them. As long as you have them handy, you should be just fine. All right, let's get to the example. That's where we left off. The sums of squares within treatments, it says the sum of the sum of squares. The reason why there's not an actual formula there is because it's the formula for sums of squares that you've already been doing. So the sum of squares formula is each x minus the mean for that group squared and then summed. Okay, that's how you get the sums of squares for each group. So once you get the sums of squares for each group, you add them up, and that's how you get sums of squares within. So it's the same sums of squares formula you've already been doing. Your degrees of freedom formulas are pretty straightforward. Make sure you recognize big N is the total number of people in your sample, and K is the number of groups. And these add together as well. Between plus within equals total. So once you collect all of your sums of squares formula and your degrees of freedom, you calculate the variance. The variance for between and the variance for within. We call that, in this book anyway, we call it a mean squared. So mean squared between is your variance for the between. Mean squared within is your variance for within. So once you get those two values, you can do your F ratio. Okay, and once you get your F ratio, that's your final step. You can compare it to the critical value. So again, this is the summary table where I encourage you to always use. It helps keep you organized, and it helps keep your calculations in check. So once you solve for each one, you plug it in the table. The values going down, these add together, and the degrees of freedom add to the total. Going across, you're going to divide. Sums of squares divided by degrees of freedom. Remember, that's always variance formula. That's going to equal the mean squared. Same thing with within. Within divided by degrees of freedom equals mean squared within. Once you get the mean squared between and within, you can calculate your F ratio. Okay? Then you're going to look up your critical value. We actually didn't get to do that in class, but you'll have a chance to do that today. You're going to need 3 pieces of information. You're going to need to know alpha first, which is usually 0.05 unless you're told otherwise. And you need to know your 2 degrees of freedom. You're going to need the K minus 1, which is your between. It's this number right here. And you need to know N minus K, which is your within. So once you have these 2 values, you look them up on the chart, and you find your critical value that way. Okay, we decided that this was 50. 80 minus 30 is 50. All right, and this is where we finished up talking about this example, which you should already have the numerical input for. I walked you through the formulas, but hopefully you got a chance to look at them on your own. If not, you're going to get a chance to do an example by hand, so you can refer back to these slides and see how these formulas were created in order to duplicate them for yourself.